So this is an NSF project to study an astronomical phenomena known as X-ray bursts, which are thermonuclear explosions on the surfaces of neutron stars. A neutron star is the remnant of a massive star that has exploded in a supernova, and it leaves behind this pretty exotic, mysterious object, this neutron star, which has a mass of about 1.5 to 2 times the mass of our sun, but a radius of only about 10 kilometers. So it's extraordinarily dense. If you took a teaspoon of this matter, it would weigh more than 1 billion tons. And in fact, it's so dense that we don't really have a good understanding of how matter behaves at the center of a neutron star. We don't have a good enough understanding of the strong force to really say what's going on at its core. And so X-ray bursts are a way of learning about neutron stars and trying to figure out what are their properties. So an X-ray burst happens when you have a neutron star that's in a binary, and there's a companion star, maybe a star like our sun, and they're so close to each other that the neutron star pulls matter off of the companion, hydrogen and helium mostly, and that basically rains down on the neutron star surface. And over the course of hours to days, enough of this matter accumulates on the neutron star that you reach sort of a critical mass, and suddenly this helium undergoes a runaway thermonuclear reaction, and you get this enormous release of energy, which is what powers the X-ray burst. So we see this release of energy as an X-ray flash in our telescopes orbiting Earth. One of the best telescopes available today to detect X-ray bursts is the nicer X-ray telescope, which is on the International Space Station. And so it has just really good photometry and time resolution and spectral resolution. And it basically collects these X-ray photons from these bursts which are happening throughout our galaxy. So there's something like 100 or so sources that show these bursts, and any one of those sources might go off on any given day, and this telescope will find it. So we're going to be doing simulations of these X-ray bursts, basically state-of-the-art simulations using a general relativistic hydrodynamics code called Athena++. And we're trying to model the winds primarily from these X-ray bursts. And there's some observations from this nicer telescope that tells us that these winds might have heavy elements that were synthesized during the burst itself, and are giving rise to spectral features and spectral lines in the X-ray emission. And so we're going to be doing these simulations to try to see if we can reproduce some of these observables and use them to better interpret the data and ultimately, hopefully, learn more about bursts, the burning process, as well as what's the properties of the underlying neutron star that's supporting the burst. I started working on neutron stars as an undergrad at the University of Chicago on X-ray bursts, and have worked off and on X-ray bursts and other aspects of neutron stars since then. So it's something that I've sort of a first love that I've always come to like coming back to. So neutron stars are fascinating objects. They are so extreme in so many ways that all different physics plays an important role, and all 4 fundamental forces, probably more so than in any other object in the universe, plays an extreme role. So the gravity is obviously very strong because they're so dense and compact. The strong force is at its most extreme. The weak force and electromagnetic forces are important if we want to understand some of the features that we see from neutron stars and in X-ray bursts. And so it's kind of a neat, fun object that we get to apply all this different physics, general relativity, quantum mechanics, hydrodynamics, and try to use all of those to understand what's going on in this star. I definitely hope to work with undergraduates and graduate students here at UTA, and the grant provides funding for 3 years for a graduate student here at UTA. And I'm also going to be working with undergraduates as part of the Louis Stokes Minority Summer Research Academy. So it's for students who are underrepresented minorities that are coming from other universities and come to the UT system, including UTA, with the hope of getting some experience doing research. So these students may not ordinarily have an opportunity to work in astrophysics and do these kinds of simulations. So it's going to be a fun chance for them to do it and learn some of this stuff, and for me to get to work with them. I'll be working with physicists at the University of Virginia, including Professor Shane Davis, who's an expert at doing simulations of creating black holes, and is an expert at doing some of these multi-dimensional radiation hydrodynamic simulations. And so we're pairing up using his expertise at the Athena++ and my expertise in X-ray bursts and modeling of that type, and trying to combine forces and make progress on this problem and make some contributions to our understanding. The department here is really active in all different areas, including many areas related to astrophysics and space physics, neutrino physics, which all play a role in our understanding of the universe. And so it's fun to be part of that group and get to hear about what everyone else is doing, and sort of this interdisciplinary way of thinking about things and hearing about others' research.